Okay, once again, hello and welcome to today's webinar, to today's central exercise session. As usual, please ask your questions on our chat channel. The chat is on chat.tum.de. And as usual, please use the channel dedicated to that, MA9711-CE. The chat will be moderated, as usual, or most of the times at least, by Leslie Fernandez.
Hello, everybody. So once again, my name is Leslie Fernandez, and I will be the moderator in the chat. So I will be keeping track on the questions that you ask, and whenever Professor Ritter stops for questions, I will bring them to him so that he can answer them.
Okay, thanks a lot, Leslie. Today we'll discuss sheet number 7. I'd like to start with sheet 7 right away, and at the end or after the end of this regular C class, I'm going to say a few words on TUM exam for the test drive tomorrow. Before I start, please also let me mention that the evaluation is still live. So today is the last day of the evaluation. Today until midnight, you can still cast your vote, give your feedback, and I'd like to welcome you very much to do that. The feedback that you give is very valuable to us and hopefully also to you, because as things currently stand, probably the summer semester will also be an online semester. So if there's any suggestions you'd like to make, you might be the first to profit from that. So once again, please, if you haven't done so yet, please give us feedback in the official evaluation. So let me start the screen sharing so you can see what I'm actually doing. Okay, so let's start with sheet number 7. Sheet number 7 is basically all about basis coordinate systems and linear mappings and the representations as matrices. So in C7.1, we start with a simple introduction that focuses on linear mappings. We have two mappings here, and the task is to decide whether these are linear or not. So starting with part A, this is a linear mapping. The domain is R3. The codomain is R. So in a way, the codomain is smaller than the domain, meaning the dimension is lower than that of the domain. And F is defined as mapping the vector x1, x2, x3 to the real number 2x1 plus x2 minus x3. And the task is to decide whether that is linear or not. So for a linear mapping, there's two properties that we need to check. The first one is f of x plus y. So if we take the sum of two vectors and then apply f to that sum, that is the same as applying f separately to x and to y, and then taking the sum of the results. And that needs to hold for arbitrary x and y in the domain, so here in R3. Okay, so what we're doing is we just take arbitrary x and y and substitute that into the function definition to check whether this property holds or not. So we'll start with let x and y be in R3. As you would expect, x is the vector with components x1 to x3, and y is the vector with components y1 to y3. And then let's compute f of x plus y. So that means we take the sum first, and then we apply f. So the sum of x and y is simply taken component-wise. So the first component of the sum is x1 plus y1. The second is x2 plus y2, and then x3 plus y3. And then we apply f using this definition. So what f does is it takes 2 times the value of the first entry in that vector here. The first entry is now this one here, x1 plus y1. So to apply f, we take 2 times x1 plus y1. Then it adds the second entry of the vector. That second entry is this one here. So we add x2 plus y2. And finally, it subtracts the third entry of the vector, this one. So in our application, this is the third entry. So we subtract x3 plus y3. So that's f applied to the sum of x and y. And now let's have a look at f of x plus f of y, this right-hand side here, to see whether that yields the same result. So what we do now is we first apply f to the vectors f1, x2, the vectors x1, x2, x3, and y1, y2, y3. And then we sum up the result. Right, so here we get f applied to x1, x2, x3. That is 2x1 plus x2 minus x3, exactly the definition, plus, and if we apply f to y1, y2, y3, that's 2y1 plus y2 minus y3, like this here. And the question is this the same as the result that we had up here? And to make comparison a little easier, let's try to sort that in a different way. So here we have the terms x1, y1, those two here. Obviously, we have 2 times x1 and 2 times y1, so we can factor out the 2 here. Then let's collect the x2 and y2 terms. We have x2 here and y2 here, so that's just x2 plus y2. And finally, the terms with an index of 3, this one here and this one here. So that is a minus x3 plus y3. And if you look at that, it's exactly the same as we had up here. So in fact, f of x plus y is equal to f of x plus f of y. So this first property holds. And for the second property, we need to take a look at a single vector and a scalar multiple of that. So we take a vector x and a scalar lambda, and we want to evaluate f at lambda times x. And the property of a linear mapping is that is the same as first taking the image of x and then scaling the result by the same factor, lambda. Okay, and that needs to be true for all x in the domain, so in R3, and all lambda in R, all possible scalars of that vector space. And again, let's say let x be a vector in R3, x1, x2, x3, and lambda be in R. Then, well, f of lambda x is then the same as f of. So we multiply x by lambda first, and we get the vector lambda x1, lambda x2, lambda x3. Then we apply f. And again, applying f means take 2 times that first coordinate, so we get 2 times lambda x1. Then add the second one, so we add lambda x2. And finally subtract the third coordinate, so we subtract lambda x3. And you can easily see there's a lambda in all of these terms here, so we can factor out lambda. And that yields lambda times 2x1 plus x2 minus x3. And if you look at that closely, you can see that is the same as lambda times f of x. So again, that property also holds. And that means we have shown that both properties of a linear mapping hold for our function f here. So the function f is a linear function. We know that f is linear. Before we move on to the next part of that question, let's see if there's any questions already, Lesuri.
Yeah, they are. So one of the questions, it's like a general question. Maybe we can answer that before we start anything else. And it's like they were wondering whether it could be possible to get the solutions of the homeworks before, so already this week and not just after the holidays or just after the Christmas break.
Yeah, so I was planning to release the answers for sheet 7 this week already. Yeah.
Okay, and then like coming to their exercises, like they were wondering whether it's necessary to write basically what means being linear. So fx plus y has to be fx plus fy, taking lambda in a real constant, whether they really have to write somehow to say the formalities, or that just like going directly to the computations could be enough.
So basically, you mean writing this here down once again?
Yeah.
So if it's clear what you're doing in your computations, it's not really necessary to write that down once again. It usually, I would write down something like this, just as a shortcut, so that the corrector knows what I'm planning to do here. As usual, this is something that probably helps you in case you go wrong in this here. Somewhere the corrector at least knows what your original plan was. Right? That's why I would quickly write down my intentions. Or at least you should write down something like, we're going to show the two properties of linear function, and then point 1, point 2, and then just go straight to these computations.
Okay, then there is another question that it says whether it could be possible to do the whole thing instead of like taking first like the sum and then the multiplication by a constant, taking like f of lambda x plus mu y could be the same as lambda fx plus mu of fy.
Mm-hmm.
So
if I got that right, what you wanted to do was something like this here. Is lambda f of x plus mu f of y. So for vectors x, y, and for scalars lambda mu, right? Yeah, so that's an alternative, so to say, to proving these two properties separately. You can, of course, also just take this property here and prove that. Yeah, if that's easier, if that's shorter for you, then by all means, that's fine.
Okay, then there is another question that it says, do you differentiate between vector space and affine space, or everything linear mapping affine functions are just subspaces of vector spaces?
So if we're working with linear mappings, those are always defined on vector spaces. So both domain and codomain are a vector space. We're not going to talk about mappings of affine spaces.
Okay, then somebody asked whether it also needs to contain the zero vector.
So what we have seen is that for a linear mapping, you always have the property that the image of the zero vector is again a zero vector. Those might, of course, look different because we might have a different vector space in the domain and the codomain, but they're both their respective zero vectors. That needs to hold. You don't have to show that, but if you can show that this doesn't hold, then you can be sure this is not a linear mapping. On the other hand, it doesn't suffice to show that a mapping is linear, right? Not every mapping with that property is automatically linear. That's not true.
Okay, now another question is, can we prove it if it's linear by mapping the zero vector? Well, I guess this was just answered. Sorry for that. Yeah, so far we can continue, and if there are more questions, I will collect them for the next break.
Okay, great. So let's continue with the second part of this, which is to compute a basis of the kernel and the image of F. Okay, so let's start with the kernel. So for a linear mapping, we can compute bases of the kernel and the image. The kernel of a linear mapping is defined in the same way as that of a matrix, basically. What you want is the set of all x vectors in the domain, so R3 in this case, where f of x equals the 0 vector. And in that case, the 0 vector of the vector space R is just the number 0. So this is the kernel, the zeros, the roots of that function, if you want. What is special about linear functions here is that the set of roots is always a vector space, and thus we can determine a basis of that kernel. But what we have to do to get that is we just have to solve that equation. So we have to solve f of x equals 0. And in that case, that is equal to solving 2x1 plus x2 minus x3 is 0. And that's a system of linear equations. There's one equation and there's 3 variables in that one. So we can choose to, for example, solve that for x1. x1 would be, let's see, minus 1 over 2 x2 plus 1 over 2 x3. And x2 and x3 would be free variables. So x3 is a free variable, x2 is a free variable, and x1 we just solved. That is minus 1 over 2 x2 plus 1 over 2 x3. And that means the kernel of f is the set of all vectors of the form minus 1 over 2 x2 plus 1 over 2 x3 and x2 and x3 for the second and third entry. And those x2, x3 are free variables, so those may take on any value in the reals. So you could also write this as usual in the form, let's collect the x2 components first. Then we have minus 1 over 2, 1, 0. And then the x3 components, that's 1 over 2, 0, 1. And finally, let's write this in the form, this is the span of the vectors. And again, we can scale these vectors. If we're talking about a span of vectors, we can scale each vector more or less arbitrarily, just not by 0. But we could, for example, multiply this by 2 to get rid of the fraction. So the span of minus 1 over 2, 1 and 0 is the same as the span of minus 1, 2 and 0. Just 2 times the original vector. And if we do the same for the second vector, then we get 1, 0, 2. So this are 2 vectors that span our kernel. And as you can see immediately, for example, by having a look at these 2 entries here, those 2 vectors are linearly independent. So that set is a basis of the kernel of f. Okay, and that is exactly what we wanted. So that's how, that's how to get a basis of a kernel. Now for the image, let's talk about the image quickly. The first thing you should always do is, if you know a basis for the kernel, or at least the dimension of the kernel already, then you should invoke the rank nullity theorem and determine the dimension of the image. As you know, the dimension of the image of f plus the dimension of the kernel is going to be equal to the dimension of the domain. The domain is R3 in this case. So that means the kernel is 2-dimensional. The image therefore has to be 1-dimensional, right? So that's 3, that's the dimension of R3, minus 2 for the kernel, and that's 1. So the image of f is 1-dimensional. On the other hand, the image of f is clearly a subset of the codomain. So this is the codomain. The codomain is R. So what we're looking for is a 1-dimensional subspace of R. R is itself a 1-dimensional space. So any 1-dimensional subspace of that is necessarily the whole space. And those here together, that means the image of F is the set of reals. And if you want a basis for that, we could say, well, this is spanned, for example, by any vector in that set that is not the zero vector. So for example, by the number 1. But as I said, any number would be fine here. Okay, so in this case, invoking this Regularity Theorem gives us the answer right away. Just to make sure that you know how to deal with situations where this is not sufficient, let me also show you how to do that in an elementary way. You could also take a basis of a domain, any basis. In this case, the domain is R3. So for example, we could take the vectors U1, U2, U3, the unit vectors. And then we would say, well, the image is necessarily spanned by the values of F on that basis. Right? Every vector in the image needs to be reachable that way somehow. So this gives you a generator for the image, but that may still be too large. And in this case, it is too large. So as you can see, we have 3 vectors here in that span. That's not a basis. It's generating the image, but it might be too large for a basis. So, but let's still compute that first. So we have span of f of u1. U1 is 1, 0, 0. U2 is 0, 1, 0, and U3 is 0, 0, 1. And if you just substitute that into the function definition, f of 1, 0, 0 is 2, f of 0, 1, 0 is 1, and f of 0, 0, 1 is minus 1. So this will span the image. And now what we have to do is we have to find a largest linearly independent subset. Or in other words, we have to reduce that set. We have to remove vectors until we get a linearly independent set. And for example, we could just remove this one here and then this one here. And for example, the 2 will remain. So again, what we get is the set of reals for the image and this here as a possible basis for the image. I think I forgot to write that up here. Yeah, so this here is also a basis for the image. And you can see I got a different result here. Both are fine. Any basis for the image will do. And yeah, depending on how you compute that, you might arrive at different results. Okay, let's see what questions you have.
The questions are, okay, there are several. So maybe we can start by, is it necessary to scale the span?
I'm sorry, I didn't get that. What is necessary?
To scale the span, I guess what they mean is that having the kernel, yeah, like going from the second equation to the third.
Yeah, so you could also take just this vector here and this vector as they are into the span. That's fine as well. You can scale them, you don't have to scale them. I just like to do that because I don't like fractions. But you're free to not do that, yeah.
Then there is another question that it says, how do you know so fast that those vectors, the ones in the span of the kernel, they are linearly independent?
So what I'm doing is I'm basically looking at these 2 rows here. And if I would try to prove whether these are linearly independent, then I would say something like I need to determine a linear combination of the 0 vectors. So I need to determine lambda 1, lambda 2, such that this is 0, 0, 0. And to prove that they are linearly independent, I have to show that setting lambda 1 and lambda 2 to 0 is the only possible solution to this. And if you look at the last line here, this one here, and you can see that that says 2 lambda 2 equals 0, so necessarily lambda 2 has to be 0. And if you look at the second line, that corresponds to the equation 2 lambda 1 is 0. So necessarily lambda 1 is 0, right? So from these two lines that contain zeros everywhere but in one position, and we have one such line for every vector, different line for every vector, I would immediately be able to conclude that these lambdas have to be 0, so the vectors are linearly independent. That's how I did that, just looking at these two lines here. And you'll notice that is always the case if you derive a solution for a system of linear equations, because for each free variable, you get a vector that has a 1 entry or a non-negative entry, a non-zero entry, exactly at the place that corresponds to the free variable, and zeros for all other free variables. So you'd always have that correspondence.
Okay, so another question is, can you explain the difference between codomain and image of a function in this specific case?
So in this specific, the codomain generally is a superset of the image. It may coincide, and in this specific case, image and codomain are the same, but it doesn't have to. The image of a function generally may be smaller than the codomain. In this case, as I said, there is no difference, because we know, for example, from this argument, we know that the image is one-dimensional, and we know it's, of course, contained in the codomain. That's the definition I just said. Well, the codomain needs to contain the image. And a one-dimensional space inside a one-dimensional space has to be the same space. You can reach every vector in R just from the image of F. And that's why in this case, there is no difference between codomain and image. But in general, there may be.
Okay, then there is another question. This one, I wasn't sure how to answer. So it says a span 1 is the vector 1, 1, 1, like a vector in R3 that is 1, 1, 1 in all elements. And I think you might be able to explain it better than me.
Let me clarify this. So what I mean here, span 1, actually, this is not, actually it is. So what I mean here is this 1 is a number, is the real number 1, right? So the span of 1 is the number of the set of all linear combinations of that 1, and the linear combination of a vector is lambda times the vector, lambda in R. So in effect, lambda times the real number 1 is just lambda. So what that is the set of all lambda in R, right? And that's R, the set of all reals. In contrast to that, I've also used this vector here. Notice we have this double stroke here, like with set notations. What I mean by that is the vector that consists of all 1 entries of appropriate dimension. And if the dimension is not clear, then I'll write an index here, like 1n. That would mean the vector has n entries. So in particular, the real number 1 would be equal to the all ones vector with just 1 entry. Right? I would identify those two. So this is the real number, and this is a vector, so that's in R to the 1 if you want. Yeah, they mean the same thing. In general, this all ones vector is larger. If we're not talking about the vector space R, but about larger spaces, R2, R3, and so on, and it has more components all being 1. So those two coincide in this case, but that's just a coincidence. In general, those will be different. One is a real number, one is a vector.
Okay, sorry. Another question is whether for the image you use the function values of the basis vectors.
Mm-hmm. What is the question?
For the image, you use the function values of the basis vectors. I'm not sure whether I really get it.
So do you just want confirmation probably? So what I'm doing is, again, I'm taking the basis of the domain. Any basis will do. So usually you take the easiest you can get away with. Like in this case, the unit vectors. And then the image is always spanned by these, right? So that's not necessarily a basis because it might still be too large. It is always a generator And in this case, as you can see, it turns out to be too large. Any of these on their own would already span the whole space. So this is a set of 3 linearly dependent vectors, obviously, and you have to reduce that set until you get linearly independent vectors to obtain a basis. But so the first step here this year will always give you a generator of the image. I hope that was the actual question. If it wasn't, then please clarify.
Yeah, then there is a question that it says, can you explain one more time how you get to 2, 1, minus 1 from function values on the last part?
I get this one here. Sure.
Yes,
So
vector,
again, the
right?
function definition, as it's on the sheet, is this here. So what I'm doing is I'm just substituting the values, right? So for example, here, for this vector, I'm substituting 2 times 1 plus 0 minus 0, that's 2. And you do the same for this vector here, that ends up with a 1 here. And for this vector here, that ends up with a 1 here. So minus 1 altogether. And that's how I get these results.
Okay, and one last question, maybe it could be like, can you explain when we can use unit vectors for determining the basis and when not? So
in this case, you're free to choose any basis you want for the domain. And the unit vectors are, of course, a particularly easy choice because the computations get easier with those. So whenever I'm free in my choice of basis, I would probably use the standard basis, the unit basis, unless I have a compelling reason not to. And there might be compelling reasons not to. But in many cases, you are not free to choose whatever basis you want. In many cases, it will be given. We'll see examples in the following problems. But if I'm free to choose anything, of course, I would choose something that is easy to work with. And the unit basis is always a good candidate for that.
Maybe one last question, because I have the feeling this one, it has been repeated more than once. Like when we say like x2 and x3 are free variables, like why are x2 and x3 free variables? I tried to answer in the chat, but maybe it would be nice to do it for everybody.
So in this case, you have like this system of linear equations. And if you solve that in the way that we always solve systems of linear equations using matrix form, for example, that would correspond to the matrix 2, 1, minus 1, right-hand side 0. And I would then try to transform it into echelon form using the first pivot element I can. That would be this one here, the 2. And of course, this already is in echelon form. There's no other equation, so there's nothing to do. But according to our conventions, what that means for the solution is now the columns that have no pivot, those correspond to free variables. So that's why x2 and x3 are free variables here. And the x1 is not, because I would solve for the elements that have a pivot using that pivot element. In this specific case, you could also have used this or this as a pivot element. It doesn't really matter. Yeah, so any other solutions would also be fine. And obviously the basis you get might look different, but it would still span the same space. It's just using the convention that we use for solving all of our systems of linear equations. And unless there is a compelling reason not to, I would try to stick to that convention.
Okay, and there are no more questions for the time being.
Okay, good. So let's talk about B very quickly. So in B, we have another function that's defined on R3, and the codomain is R2 in this case. And the definition is f of x1, x2, x3 is defined as x1 minus x2 and 1. Now in this specific case, it's very easy to see that this is not a linear function. The one thing I would always do first, if I have a function, at least quickly in my mind, is try to substitute the vector 0, 0, 0, the all zeros vector, and see what the result is. The result has to be the zero vector. Otherwise, the mapping cannot be linear. We just established that before. In this case, what I would get is 0, minus 0, and 1. So this is obviously not the zero vector in the codomain in R2. And that means the mapping cannot be linear. And thus I'm done with that problem already. Okay, and of course, if the function is not linear, then we don't have to determine a basis of the kernel and of the image of the function anymore. And in general, we can't. So of course, we could determine the set of roots and we could determine the image by other means, but there usually is no basis for those, as they are not vector spaces in general. They are for linear functions, they might not be for general functions. So we're done with B.
Yeah, there are questions. One is, if we just, for B, if we just prove that F0 is not 0, we prove that it is not linear, that could be enough?
Yes, so this is enough in this case. We prove that it's not linear just by proving that f of 0 is not 0. Of course, there are functions that are not linear, but that still have this property. Yeah, so that excludes linearity already. But if that property would hold, then it might still be that the function is linear or not linear. We wouldn't know.
That's it for the time being.
Okay, great. So let's go on with C7-2. So in C7-2, we have two vectors. We're calling those B1 and B2, and we have a vector space V that is spanned by those two vectors. And they have the coordinates 2, 1, 0 and 0, 1, 1. And those vectors are called B1 and B2. And we also have a linear mapping, but yeah, we have linear mapping, right? Yes, that's defined on V. And the codomain is R3. And a linear mapping can be defined by giving the values of the linear mapping on the bases, because every other vector can be expressed as a linear combination of the bases. And then by linearity, we can compute the corresponding image. We do that in part A. So here, the image, the function, sorry, is actually defined in terms of its image on the basis vectors. So here, f of B1 is by definition 1, 2, 0. And f of B2 is defined as 1, 1, 0. And the first task is to use that definition to determine f of 2, 2, 1. Now what we have to do there is, we know the function values on B1 and B2. We don't know anything else. We know that B1 and B2 are a basis of that vector space V. So what we can do is, we can try to express 2, 2, 1 as a linear combination of B1 and B2. And then we just use linearity. So to do that, we take this vector 2, 2, 1, and we write that as a linear combination of B1 and B2. And remember, B1 is 2, 1, 0, and B2 is 0, 1, 1. Right, so this is B1, this is B2, and we want to determine the right values for lambda 1 and lambda 2. Now, if you look at the first line here, you can see that the value of the first row is determined by lambda 1 alone. So it's 2 times lambda 1, then 0 times lambda 2. So if you want this 2 here, then lambda 1 necessarily has to be 1. And if you look at the third row, then you can see that this value is determined by lambda 2 alone. So this is the equation 1 equals lambda 2. And of course, we have not looked at the second row yet, and we have to do this to make sure that we actually get a feasible solution here. Now we're looking at that here. If we compute lambda 1 plus lambda 2 with these values here, then we get lambda 1 plus lambda 2. 1 plus 1 is 2, and actually there is a 2 in here. So the second row is also fine, and we have found a solution of that equation system. And of course, we always find a solution if the vector is actually in the space V, yeah, as given here. If it's not, then we might not find a solution, or we will not find a solution. So we have established our linear combination here. And now we can just use linearity. So what we know is now that f of 2, 2, 1 is equal to f of 1 times b plus 1 times b1 plus 1 times b2, sorry. And by linearity, this is the same as 1 times f of b1 plus 1 times f of b2. And then, of course, we know f of b1 and f of b2. So by definition of that mapping, f of b1 is 1, 2, 0. Right, so that is f of b1. And f of b2 is 0, 1, no, sorry, 1, 1, 0. That's f of b2 here. So we can easily compute the result. That is, let's see, 1 plus 1 is 2, 2 plus 1 is 3, and 0. So this 2, 3, 0 should hopefully be the image of that first vector. And of course, the second one can be dealt with in exactly the same way. So if we're looking at the vector, what was that? 4, 0, and minus 2. Then again, we have to find coefficients such that 4, 0, and minus 2 is equal to lambda 1 times our first basis vector, that was 2, 1, 0, plus lambda 2 times our second basis vector, that was 0, 1, 1. So this is B1, this is B2 again. And again, you can just look at that system and see, well, the only possible solution for lambda 1 is 2, because I need 2 times 2 to get the 4 here. Lambda 1 is 2. The only possible solution for lambda 2, determined by the third line here, is minus 2. And then if I use those and check whether this is actually a feasible solution using the second line, I get 2 minus 2, and that is 0, and that's actually correct. So again, I can compute the image of that vector by using linearity. That's 2b1 minus 2b2. So that's the same as 2f of b1 minus 2f of b2. And I do know those images already. By definition, the first image is 1, 2, 0. And the second image, sorry, minus b2, of course. The second image is 1, 1, 0. So again, this is f of b1. This is f of b2. And the result is then 0, 4 minus 2, that's 2, and 0. And hopefully that was correct. Okay, questions so far?
Okay, so questions that's one question would be, could you please explain why we use b1 and b2 and not the values of the function?
I'm afraid I don't really get the question.
Yeah.
Maybe you can let me know where this exactly refers to.
Yeah, maybe you can rephrase that maybe better. And then we have another question. What do we compute in part A? And well, I was just answering. Part 10, we compute the values of the function evaluated in these two vectors, 2,
Right.
2, 1, and...
Right. So we answer the question. I mean, the question is to determine the value of the function at a certain point or at two certain points. And that's exactly what we're doing here. And we
But
have to use the definition of that. That is a little unusual. So the definition of a function is by its values on the two basis vectors b1 and b2. So we have to make use of those values somehow, and that's what we're doing in part A.
okay, so now could you please re-explain where are you getting the vectors from that you use to calculate the image? I guess this is from what we calculate the function, right?
So yeah, so the vectors that I use to calculate the image, once again, so this is given. This is the vector I want the image of, and I am also given the values of f on these two basis vectors. That's part of the problem statement, and that's what I'm using. What I'm doing is I'm determining a linear combination that represents my input vector using these two basis vectors. And then again, I'm using linearity. If I have that linear combination, I can express my desired vector as this linear combination. I can then use linearity of the function. And that means I can express the desired image as a linear combination of these images, f of b1, f of b2, and I know those by definition. Those are given in the problem statement. I just use those and do the computations. That's the whole idea here.
Okay, and the same person did rephrase the question we didn't understand, and it says, why do we take b1 and b2 to get the lambdas and not its results of the function? So why b1 and b2 and not fb1 and fb2? This is what I understand.
Okay, so what we need to do again is compute the image of this vector here. The vector lives in the domain. So if you want to find a linear combination of that, we need a basis of the domain, and the basis of the domain is given by b1 and b2. So this is not a vector in the codomain, in the image yet, right? We need a basis of the domain to express that, and this is why we take b1 and b2. It's not a vector in the image, or it's not given as a vector in the image.
Okay, and one last question is, what does it mean if there are no lambdas possible to reach the objective vector? That means if the vector is not a linear combination from b1 and b2?
Okay, so in this case, if we can't find lambdas like this, or if we find that this is not feasible due to the second row, for example, then this will show us that the vector is not actually a linear combination of b1 and b2. And by the problem statement, that means that the vector is not actually contained in V, because V is defined as the set of all linear combinations of b1 and b2. So if a vector is not a linear combination of those, it is not in V. Right? So in this case, that would tell us the vector is not in V, it's not in the domain, so the function is not defined for that vector. And we could not determine a reasonable image then. So that would render the whole thing pointless.
Okay, maybe there is one more question that there is somebody confused because in a school they learn that the linear function can have a constant in the formula, but here it can't because it doesn't have the zero vector in it, and thus it is not a linear mapping.
Okay, okay, to clarify this, a linear function cannot have a constant at it. I know that is often taught in school, but it's wrong. Or let's say at least it's a misuse of terminology. So what you learn in school is a function of that form here, whether you call it m and t or whatever else. So m and t are parameters, and a function of that form, you call that linear in school. That is not generally a linear function. Of course, unless t is 0. That's why I'm calling these affine linear functions, to clarify that a little. Yeah, so this is not a linear function. It would be an affine function. We're not talking about affine functions in general, but functions of this kind that map from R to R, from the reals to the reals, I'll call those affine linear functions. To clarify that they are related to linear functions, but they are kind of linear functions plus a translation. And that makes them nonlinear. They're still similar to linear functions in the way that affine spaces are similar to vector spaces. Yeah, again, you have that translation here that makes it different. But we're not going to discuss this in more detail. But please remember, this is strictly speaking not a linear function, and it's not a very good idea to call them linear functions in school. But unfortunately, it's hard to lobby against the school books here. But that is not standard usage in mathematics. Please, if you have a function like that, please don't call it linear. Call it affine linear if you want, or anything else, but not linear.
Okay, and for the time being, there are no more questions.
Okay, good. Then let's move on to part B. So in part B of C2, we are asked to compute the basis of the image and the basis of the kernel of F. And well, let's do that. So we'll start with the image. Obviously, the image is again spanned by the values of F on a basis. So in this case, we have B1, B2. That's the basis of V. So that means the image of F is the span of the values of F on that basis or on any other basis. In this case, that's the easiest choice that you have because you know the values of F on that vectors, on that basis vectors already. If you would take something like standard basis, which might not even be possible for this vector space V, then you would have to compute the right values first. And we don't really need to bother. So we know these already. And we can just use that. So the span here, F of B1 is 1, 2, 0. And F of B2 is, I think, yeah, 1, 1, 0. So this is two vectors that span the image. And if you look at those, again, just take the last two rows here, you will see, sorry, not the last two rows, bad idea. Take the first two rows. You should be able to see that those are again linearly independent. If you don't see that, then of course you're free to try Gaussian elimination on those, like just subtract the first row from the second one 2 times, and you get something like 0, minus 1, 0, 0. And now you can see that those are linearly independent. 2 pivot elements, the rank of the matrix is 2, so the 2 columns are linearly independent. Okay, so this is a basis of the image of F. And now we can see that the image of F is 2-dimensional. That was not part of the question, I think, but still it's worth to note that, because that will be helpful for the kernel. If we want to compute the kernel, again, please, if you have the information, invoke the Regularity Theorem first. So here, the dimension of V of our domain is the same as the dimension of the image of F plus the dimension of the kernel of F. The dimension of V is 2. The dimension of the image is 2. So, well, what is the dimension of the kernel? It needs to be 0. And what does that mean? Well, that means the kernel itself consists of just one point. And that one point has to be the 0 vector then, right? F of 0 is always 0, so that is always in the kernel. And if the dimension is 0, then it consists of just one point, that is the 0 vector. So we need to take the 0 vector of the domain, and that's just 0, 0, 0. And by convention, as you hopefully remember, we defined a basis for that to be the empty set. So that's the solution of part B. And again, invoking the Regularity Theorem means you don't have to do any more work in this case. Yeah, so that's always a good idea to try that first. Even if it doesn't give you the right result right away, it will give you the dimension. So it will help you check your result later on, or even help you with your computations. So, questions about this one?
So the first question is it possible for two different vectors in V to map to the same point in F with a given coordinate B?
Is it possible, so if we have 2 points in V, could they map to the same point in the image? Is that the question?
Yeah, I think this is what they are asking.
So
yeah.
in general, that might be possible, yes. In this case, it's not, because the kernel just contains a 0 vector. And if we have two different values, so if we have like an x and a y that have the same value, then that would automatically mean that f of x minus f of y is 0 vector. So by linearity, f of x minus y is the 0 vector. Right? And in this case, or in general, this means x minus y needs to be in the kernel. In this case, the kernel consists of just the 0 vector. So here, so anything up to this point is general. In this specific case, that would mean x minus y is the 0 vector, because that's the only vector that is in the kernel. So x needs to be equal to y. Or in other words, more general, the function f is injective if the kernel of f consists of just the 0 vector, and vice versa.
Another question is, if f of b1 and f of b2 are linearly dependent, could the dimension of the image of f1 would be 1?
Yes, so if f of b1 and f of b2 would be linearly dependent, they're not in this case, but of course that could happen, then the dimension of the image would of course be lower, and in this case it would be 1, yes. Unless they are both a 0 vector, then the dimension would be 0.
Then how do you proceed if the dimension of the kernel is not 0?
So if the dimension of the kernel is not 0, then I have to compute the kernel, obviously. And that means in this case, so if I were to compute the kernel, let's say, again, I have to come up with all vectors that map to 0. So the question is which vectors would map to 0. So let's say I have a vector x in the kernel. Then that would mean there exists lambda 1, lambda 2 in R, such that first, x is a linear combination of b1 and b2 with these coefficients here, because b1, b2 is a basis of v. And f of x would be 0, a 0 vector. So these two things together would mean lambda 1 f of b1 plus lambda 2 f of b2 needed to be the 0 vector. And there's an equation system. I could solve that for lambda 1, lambda 2. And that solution would then give me all possible x values in the kernel. So that's how I would proceed if I didn't know the kernel was 0 dimensional. And yet, as you can see, this will only be relevant, as will only happen if those two vectors, f of b1 and f of b2, if those are linearly dependent, right? Only then can there be a solution to this that is not setting both of these lambdas to 0.
Another question is, why is the kernel, the zero vector is the dimension of kernel is equal to 0?
So the dimension is always the size of the basis. In this case, by convention, the basis of this vector space is the empty set. The size of the empty set is 0. So that's why the dimension is 0. Not much more I can say there.
Yeah. Could you also compute the basis of the kernel without the theorem?
The basis, yeah, well, as I just outlined it, yes, of course, I could do that. If I want to compute the basis of the kernel, all this here works without the regularity theorem. It's still useful to have that. So then when I get my result, I can check whether the dimension of the result is actually the correct one, the one I was expecting. But I don't need that.
Okay, there are two more questions. One is like, why did we calculate the image of F in question A? Well, we needed it, right?
Because it was required in the problem statement. Compute the basis of image F. That was part of B, actually.
Yeah, and then for the basis of the image of F, can I also take the calculated vectors from A?
The calculated vectors from A. So as long as you know that the two vectors that you had in A, so 2, 2, 1 and 4, 0, minus 1, if you know that those form a basis of V, then of course you can also take that. But you have to make sure that this is actually a basis. Otherwise, you might not get enough image vectors. You might only get part of the image. So any basis of V is fine. And the one that is readily available here is B1, B2. So in my opinion, it wouldn't be a very clever idea to take anything else, because anything else requires computations. And even if you have done those computations already, they might be wrong. And if there's an error in those computations, this will propagate. So why not just take what is given in the problem statement? We can be reasonably sure that there is no error in that.
There are no more questions.
Great. So let's move on to 7.3 then. Okay, so here we have, again, two vectors and a vector space spanned by those two, similarly to the problem we just discussed. This time the vector space is called U. And it's spanned by two vectors with not so clever naming. I named them U1 and U2, but I didn't mean the unit vectors, so that's why I say the naming was not so clever, but I'll still keep to that now. So the first vector is 1, 0, 1. And the second vector is -1, 1, 0. Those are called U1 and U2 here. And they define a coordinate system. The coordinate system is called B. Basically, a coordinate system is just a basis plus an order of the basis vectors. So U1 is the first vector of the basis, U2 is the second one. And then we have a coordinate system. And the first thing we ask for is determine the vector V that is given by its coordinates. The coordinates of a vector, we write it in this way here. So we write brackets around the vector, and then the coordinate system or the basis as a subscript. And the coordinates of that vector are 1 and -1. And what that means is simply the vector can be expressed as taking 1 times the first basis vector, U1, plus -1 times the second basis vector, U2. So the coordinates are just the scalars that you have with respect to the coordinate system that you have given. So this refers to the first vector, this refers to the second vector. And what we get here is, well, 1 times U1, U1 is 1, 0, 1, plus -1 times U2, U2 is -1, 1, 0. So the result here should be, let's see, 1 plus 1 is 2, -1 and 1, hopefully. Okay, I get something wrong here. No, seems correct. Okay, any questions?
No, for the time being, there isn't anything.
Good. So let's move on to part B. The other way around, now we have given a vector in R3, and we are asked for the coordinates of that vector with respect to B. So in this case, the vector W is -1, 3, 2. And we are requested to determine the B coordinates of a vector. So basically, we just have to reverse what we just did. We have to find a linear combination that does the right thing here. So we have to find λ1, λ2 in R such that our vector W, this one here, is equal to λ1 times our first basis vector, 1, 0, 1, plus λ2 times our second basis vector, -1, 1, 0. So this is our basis vector u1, this is our basis vector u2, and that means we just have to solve a system of linear equations once again. So let's see if that works. Again, we could just have a quick look at that system and see this last row already determines λ1. So λ1 is 2 here. The second row determines λ2. So λ2 is 3, and let's hope it all works out. And we need to check the first row as well. Now, if we substitute these values here, 2 times 1 is 2, plus 3 times -1, it's 2 minus 3, that's -1. So that also works out. And that means we have found a linear combination, or the only possible linear combination, that determines our vector W. And those coefficients, those are now the coordinates of that vector. So this here is the first coordinate, the one that corresponds to u1. So we need the 2 here. And this is the second coordinate that corresponds to u2. So we write that in the second position because u2 comes in the second position in our coordinate system. That's why the order matters. Okay, so these 2, 3, those are the coordinates of that vector. And as you can see, by the way, the coordinates, those just consist of 2 entries, not of 3 entries, even though we are in the vector space R3, but that space V is just a 2-dimensional subspace. So of course, it's sufficient to have 2 coordinates to describe every point in that subspace uniquely. Any questions yet?
Yeah, there is a question that it says, what is the difference between the vector space U and V?
And V, so V is a vector space in 7.2 and U is a vector space in 7.
Like Bavaria, but this is the
Oh, B, okay, yeah, sorry. So B is not a vector space at all. B is just an ordered set of 2 vectors, a basis. And U is the vector space spanned by that basis. So they are closely related, but strictly speaking, U is a vector space and B is not. It's just 2 points.
No more questions.
Any more questions? No more questions?
Sorry, no more questions.
Okay, great. Then let's move on. Running out of space. C. Okay, so in C, we're moving to a different coordinate system, B prime. That's the coordinate system U1 minus U2 and U1 plus U2. So we can just do the computations here and say, well, U1 minus U2. U1 is again 1, 0, 1, and U2 is minus 1, 1, 0. And U1 plus U2, that would then be, would then be this vector here. So we will get, let's see, 0, minus 1, 1. And, oh, sorry, that was wrong. My bad. We will get 2, not 0. 1 minus 1 is 2, minus 1 and 1. The rest is correct. And here's the 0. So 1 minus 1 is 0, 0 plus 1 is 1, and 1 plus 0 is also 1. So this is a different coordinate system for V. Again, you can easily see those are linearly independent vectors. So that is a basis with an order. So we have a coordinate system. And now we again asked to determine the coordinates for a certain vector. So V is given as VB in terms of B coordinates as 1, 2. That means we can easily determine the vector V behind all this, because that is 1 times U1 plus 2 times U2. So we get 1 times 1, 0, 1 plus 2 times minus 1, 1, 0. So we have, let's see, 1 minus 2 is minus 1, 1 plus 2 is 3, and 1 plus 0 is 1. So that's the actual vector V. And now we want the coordinates of V with respect to B prime. So these two vectors here, what we have to do to get that is we have to represent this vector V here, minus 1, 3, 1, so that's V. We have to represent that as a linear combination of these two basis vectors, 2, minus 1, 1, and 0, 1, 1. So we have to find the correct values for lambda 1 and lambda 2. And once again, we're in luck here. So we have a row that contains just lambda 1. So we can easily infer that lambda 1 here needs to be minus 1 over 2. And with that, we can then move on to, let's say, the second row here with minus 1 over 2 as a value for lambda 1. We have plus 1 over 2 here, plus lambda 2. So that means, oops.
Sorry, Michael.
Yeah.
There is a little typo there where you have written minus 131. It should be minus 121.
It should be my, yeah, you're of course right. Yeah, thanks a lot.
Yeah, and I thank the students that they realize and said it on the chat. Thank you.
Okay, so thanks a lot to the students. So that should be a 2. You're right. Let me mark that so that no one gets that wrong. So I just corrected this here. And of course, I also have to correct it here then. That should be a 2. You're right. I didn't use that yet. I was just about to. Okay, so let's say lambda 2. Lambda 2 is then, let's just write this equation down. So 2 minus lambda 1 plus lambda 2. So that means lambda 2 is 2 plus lambda 1. Lambda 1 is minus 1 over 2. So that's 2 minus 1 over 2. And that means we get 3 over 2. Okay, so lambda 2 is 3 over 2. And let's quickly check whether that works out for the third row as well. So we have minus 1 over 2 plus 3 over 2. That is plus 1. And luckily, there's a plus 1 here. Okay, works out nicely. So that means our coordinates with respect to B prime are then minus 1 over 2 and 3 over 2. So hopefully that's still correct. Yeah, seems to. Okay, questions?
So far there isn't any.
Okay, wonderful. Let's proceed with the last problem here. Part D. So in part D, we want to determine the basis transformation matrix. So we want to determine the basis of the transformation matrix that transforms vectors given in B coordinates to vectors given in B prime coordinates. We write that this way. So the right basis is always the input basis, because if we compute a matrix vector product, we usually multiply the matrix with the vector on the right. And this is the output basis B prime. So this matrix will do exactly the computations that we just did by hand for all possible input vectors. So of course, we can also use that to solve the problem that we have seen in part C. How do we get that matrix? Well, what we have to do here is, as for every matrix that represents a linear mapping, what we have to do is we have to take a basis of the domain and take this, of course, here. And we then have to compute the images of that basis under the linear mapping. And now for the transformation matrix here, that linear mapping is just the identity. That identity is the mapping that does not change the vector. So the vector we give it as its input is exactly the same that it outputs. The only difference here is that we require the image to be with respect to B prime coordinates. So we are doing the coordinate change here, but we're not changing the vector. And the way to get a matrix like this is always to take a basis, the input basis. So in this case, we have this basis B here, input B, or input basis B rather. Remember that basis was, where did I write that down? Somewhere here, 101 and minus 111. So that is 101 minus 110, right? Right. And what we do is we compute the images of the basis vectors under the linear mapping, in this case, under the identity. And then we express them in B prime coordinates. And each of these input basis vectors then gives us one column of the matrix that we're looking for. So this will yield the columns of our desired matrix, TBB prime. So we need to start with the identity of 101. Well, that is, of course, 101. So that's the easy part here. And then we express that in B prime coordinates. Again, B prime, let's see, we computed that somewhere. Yeah, here's B prime. Let's maybe copy that. So remember that is B prime here. So we want to express our vector 101 in terms of B prime. So we want that as linear combination of 2 minus 1, 1 and 0, 1, 1. Okay. Now, again, we just look at the first row here. It's easy to see that we need lambda 1 to be 1 over 2. And then if we look at the second row, we get minus 1 over 2 plus lambda 2 is 0. So lambda 2 has to be 1 over 2 as well. And if we check that with the third row, then we get 1 over 2 plus 1 over 2, that's 1. And actually 1 is correct. So the coordinates here, 1 over 2, 1 over 2, yield the correct result. And that means this vector here, 1, 0, 1, is in B prime coordinates expressed in this way. So 1, 0, 1 in B prime coordinates is 1 over 2 and 1 over 2. So this here is column 1 of our desired matrix. And we can do the same thing for the second basis vector. So the identity of, what was the second one? 1 minus 1, I think, right? Where do I have that? Yeah, minus 1, 1. Okay, minus 1, 1. So the identity of minus 1, 1 is, of course, also minus 1, 1. And again, we need to express that as linear combination of the B prime vectors, 2 minus 1, 1, and 0, 1, 1. And again, we can just look at the first row. Obviously, we want lambda 1 to be minus 1 over 2, so that this works here. Now, if we have a minus 1 over 2 here, then that means the second row has a 1 over 2 plus lambda 2 is 1. So we need to make lambda 2 plus 1 over 2. And in the third row, we'll then get minus 1 over 2 plus 1 over 2, that's 0, and 0 is just the right result. So these are indeed the correct coordinates. So that means minus 1, 1, 0 in B prime coordinates is minus 1 over 2, 1 over 2. And this is going to be the second column of our desired matrix. So now we have all these two columns here. That means T, B, B prime is equal to, let's see, the first column was 1 over 2, 1 over 2. And the second was minus 1 over 2 and 1 over 2. So this is a transformation matrix. Now let's verify that our computation actually works. Last step of the problem. If we want to compute, sorry, just a second. Yeah, we have this VB, we want VB prime. So this is then the same thing as the transformation matrix times the B coordinates of V. Those B coordinates are given as 1, 2. So we have our matrix. Let's factor out the 1 to make the writing a little easier. Times VB, that is 1, 2. And then the result here is, let's see, 1 minus 1 over 2 and 3 over 2. And hopefully that is the same thing that we got before. It is, I'm relieved. Okay, good. So again, we get the correct result. Of course, that computation did take a little longer. It will pay off if we have to do more of these transformations, because then we just do matrix vector computations. We don't have to recompute the matrix once again. So let's see what questions you have.
Okay, so the first question is, could be also possible to compute the transformation matrix by using a similar method as we computed the inverse matrix just by using B and B prime and not a unit vector on the one side?
So what you can do is it's pretty easy to compute a transformation matrix between the standard basis containing unit vectors and any other basis that is given. You can basically just write that down. And of course, you can then combine those matrices or the inverses to get the correct transformation matrix. Do I want to go into details here? Maybe I should. Actually, maybe we'd rather do this in 7.4. I'll discuss the details in 7.4. Let's do it this way.
Okay, there is another question that it says, can we skip the step where we multiply U1 and U2 with the identity matrix and instead directly translate it into B prime coordinates?
Yeah, of course. I mean, this step here is rather trivial, so you could just not write this down. That's fine.
Another question is, can we first compute b t b prime and then get the other with the inverse?
Of course, if you find it easier to compute t b b prime, so you can of course do that. You can compute t b b prime and then invert that to get the reverse transformation. That's also fine.
And okay, the last question is, can you please show the beginning of D again of your notes?
The beginning of D in the notes. Again, I'll upload those notes right after the end of this class. So you'll have a chance to correct your lecture notes then.
Well, now that you mentioned this, maybe I can bring a general question that it was written before in the chat, that it says, would it be possible to upload this central exercise session before tomorrow so we can watch it before the text exam of tomorrow?
Yes, yeah, of course. I upload the central exercise session. So I upload the lecture notes right after this. I'll also upload the suggested solutions right after this. The video might take a little longer because I have to edit that first, but sometime tonight it should be available.
And maybe while somebody copies part D, we can also answer already concerning the exam. Is there such a thing as error carried forward? So if there is a small mistake, for instance, for getting a minus, but the method is correct, do we still get points?
So that depends. It depends on how the question is asked. There will be questions where I'm just asking for the result. And then, of course, it doesn't really matter how you obtained that result and what errors you made. If the result is not correct, then you will not get points. If it's slightly off, and you might still get some points, but that will depend on the concrete problem. In other questions, I will ask for a justification or a documentation of your solution approach. And then, of course, you will receive points on the single steps. And if you make a mistake there, then you will usually also receive points following that mistake. So for consecutive errors, you might still get points. Again, that depends on the specific case. I mean, if the error makes the problem trivial, then of course you might not get any more points going forward, right? Something like if you mix up pi with 0 and then all the products in the following just are 0, then of course that will not earn you any more points. But usually, yes.
Okay, and maybe one last question. It's very short. Are the topics from this week part of the exam tomorrow?
I think. Ooh, I forgot the exam questions. I think I mainly did game theory there, so no.
Okay, and there is a question that it says when we are going to get more details about the exam tomorrow.
Right after the central exercise class. So I'm going to quickly go through 7.4 if you don't mind, and then I'll give you some more details on the test drive tomorrow. I try to keep that quick. Okay, so here we consider a linear mapping. Let's go to 7.4 right away. We have linear mapping F from R2 to R3, defined as F of x1, x2 is x1, x1 minus x2, and x1 plus x2. And in part A, we also have two possible coordinate systems, one for the domain and one for the codomain. And in this case, the domain and the codomain are different, so we need two different coordinate systems. We can't do with the same one. So here we have B equal to 1, 0 and 1, 2. And so that's the coordinate system for the domain, obviously. And we have B prime, that is 0, 0, 1, 0, 1, 1, and 1, 0, 1. And that is a coordinate system for the codomain R3. Okay, so the question in A is determine the matrix representation of F with respect to these two bases. So we have B for the domain and B prime for the codomain. And one possible way to do this is basically the same as we just did. We compute the images of the basis vectors under F and then express those in terms of the coordinates that we want in the codomain. So the first basis vector is this one here, 1, 0. So we could just compute F of 1, 0. If we substitute that into the function definition, this one here, then we will get, let's see, 1, 1, and 1. So that hopefully makes it a little easier. And then we want to express this in terms of B prime. So B prime is these three vectors here. I want to find the right coefficients for that. So let's see if we can do this without any intermediate computations. The first row is very simple. It just has a coefficient here. So to get this, to get this 1 here, we need a 1 here. Then if we look at the second row, that's also very simple. Also almost everywhere we have zeros except for this place here. So if you want a 1 here, we need a coefficient of 1 here. And finally, the last row, we have 1 plus 1. So we have 2 already. We want a 1. So to get that, we need to put a coefficient of -1 in front of this vector. And we get -1 plus 1 plus 1. That's plus 1. Okay, so this -1, 1, 1 will then be the first column of the desired matrix. And let's fill this in right away, maybe. So here we then have -1, 1, 1. And the order is, of course, the same order as here in B prime. And for the second basis vector, that is 1, 2. So this here is the second basis vector, 1, 2. We have to do the same thing. At first, compute the image. The image is, let's see, to go back to that one quickly. So that's 1, then x1 minus x2. So it's 1 minus 2, that's -1. And x1 plus x2, that is 3. So this is the vector we want. And again, we need to express that as a linear combination of those three vectors here. And to do that, let's see, we again need to take this vector here once to get this one here. Then for the second row, we need a -1. We can only get this from this vector here. So we need a -1 here. And now we'll have to find the right coefficient for the third row. So we have -1 plus 1, that's a 0. We want a 3. And that means we have to put a coefficient of 3 here to get this right. So the second row, the second column of our transformation matrix is then 3, -1, and +1. So this is the matrix representation that we're getting here. Let's quickly use that matrix representation in parts B and C to do some computations, and then I'll answer questions. First one we want to compute, we want to compute the value of F at 2, 1 using the matrix representation. Now remember that matrix representation works on B coordinate vectors. So first we have to do is we'll have to find the B coordinate vector corresponding to 2, 1. And that B coordinate vector is obtained by finding the right linear combination, as we did before, of these two basis vectors. Again, that system is easy to solve. We just look at that second row first. We need a 1. We can only get that with this coefficient, so that means we have to put a 1 over 2 here. And we need a 2 here. So we already have 1/2. So that means we need 3 over 2 as the first coordinate. So that means this desired coordinate vector here, B coordinates, is 3 over 2 and 1 over 2. And then what we have to do is we have to multiply that with our matrix representation. So f of 2, 1. To get that, we use this matrix representation here and multiply that with the coordinate vector that we just computed. So in other words, the matrix was -1, 1, 1, 3, -1, 1. And we want to multiply that with, sorry, not 2, 1, of course. We want to multiply that with 3 over 2, 1 over 2. And let's see, that will yield -3 over 2 plus 3 over 2. That is a 0 here. Then we get 3 over 2 minus 1 over 2, so 1. And finally, 3 over 2 plus 1 over 2, that is 4 over 2 or 2. So this is the vector that we get as a result. Remember, this is still a B prime's coordinates vector. So we have the result in B prime coordinates right now. If we want the result in standard coordinates, then we still have to transform this. Right? So if you want that in standard coordinates, then we need to compute that by saying, well, I'm taking 0 times the first vector in my basis B prime. So that is 0, 0, 1, plus once the second vector, 0, 1, 1, plus 2 times the third vector, 1, 0, 1. And that will give me, let's see, 2, 1, and 3, I think. Yes, hopefully that's still correct. So this would be the result. And of course, if it's not specified whether the result is wanted in terms of B prime coordinates or not, then this is a totally valid answer. You should maybe mention that this is given in B prime coordinates, but there's actually no need to compute this vector anymore. I just did that for clarification. Okay, and finally, let's quickly talk about image and basis. That's part C. Remember, we have that matrix here. PB prime, that was, where did I have that? Here, -1, 1, 1, and 3, -1, 1. So if I want the image of that mapping F, then the image is spanned by the columns of this matrix. So the image is equal to the column space. Again, that would then be represented in B prime coordinates. So the image of F is equal to the span of -1, 1, 1 and 3, -1, 1 in B prime coordinates. And again, we'd have to make sure that this is actually a set of linearly independent vectors, but in this case, it's easy to see it is, right? So this is actually a basis of the image of F, again, in B prime coordinates. And if you wanted that not in B prime, but in standard coordinates, you could, again, obtain the corresponding standard coordinate vectors using the same method that I did in part B. Same thing applies to the kernel. So for the kernel, I'd have to solve a system of linear equations. Specifically, I'd have to solve the system, sorry. This matrix here times x1, x2 is the 0 vector. And if I'm going to do that, I will immediately get the result either by just looking at it or by solving it or by invoking the Regularity Theorem once again. So in this case, the dimension of the domain is R2, the dimension of R2 is 2, so that's the domain. I already know the image. The dimension of the image is also 2. And that means I can compute the dimension of the kernel right away to see that this is, again, a 0-dimensional kernel. So as before, the kernel of F is simply the 0 vector. And that means a valid basis for that would be the empty set. Okay, so we don't have to do a lot of computations. Of course, if that was not the case, I could simply solve that system of linear equations and I would get the kernel. And if I do it this way, I would get it in terms of B coordinates. The kernel lives in the domain, so this is in terms of B coordinates then. Again, if I wanted that in standard coordinates, I just have to do the computations like I did before to obtain the corresponding standard coordinate vectors. So this pretty much completes C7-4. I was a little quick, probably. Questions?
There is just one question. Is it possible to form every basis just with the help of the unit vectors to exclude erasing computation faults?
Of course. So you can form any vector with the help of the unit vectors. More generally, you can form any vector in a vector space with the help of any basis you want. So of course, you can also use the unit vectors as a valid basis here. If that helps, you're free to do that, certainly.
Another question says, what are the standard coordinates?
So when I say standard coordinates, what I mean, or canonical coordinates, what I mean is the coordinates induced by the unit vectors as a basis. So if I'm using the vectors 1, 0, 0, 0, 1, 0, 0, 0, 1, or higher dimensional equivalents of those, that is standard coordinates or canonical coordinates.
Another question. Do you hear me?
Yeah. Yep, I hear you. Yeah.
So the basis of the kernel in a standard coordinates in this case is also the empty set.
The basis in this case is also the empty set because, again, the kernel consists of just the 0 vector. So the kernel that consists of just this one point, the 0 vector, always has the empty set as its basis. Yes.
Okay, there is a confusion that it says, so is B prime T B, so the transformation matrix in B prime coordinates?
Sorry, I didn't get that question. The transformation matrix?
Yeah, the transformation matrix from B prime to B, like, so B prime T B in B prime coordinates.
So the transformation matrix always refers, so you provide the input coordinates and you provide the output coordinates explicitly to get a transformation matrix. So a transformation matrix like the ones we've seen before, like for example, a transformation matrix like this here, always means the input vectors have to be given in B coordinates and the output vectors have to be given in B prime or will be given in B prime coordinates. So you always need two coordinate systems to define such a transformation matrix. I'm not sure if I got the question right, actually, but I couldn't think of a better answer yet.
There is a question that I'm not sure. It says, so I will literally read it. In the last sign in 7.4c, the sign for empty set or the 0 vector? Is the last sign.
So this one here is meant to be the empty set. That's my notation for the empty set. You can also use this if you prefer, or I usually use this here. Oops.
And one more question is, so
just a second, the 0 vector in contrast, that would be this, or just the 0. So this I would use for the 0 vector. Okay, sorry.
yeah, no, One last question. It says, why is the image equal to the column space of the representation matrix?
So you can get any vector in the image by taking this matrix here and multiplying a vector here, right? So if you take, if you compute the image, you compute the image of a basis of the domain, and then this will span the image of your function. And that's exactly what we do here. So if you take a basis of the domain, insert that here, then you get linear combinations of these columns here, right? Each vector you substitute here will give you a different linear combination. And the easiest thing you can do, once again, is to just have the vectors 1, 0 and 0, 1 here. So if you multiply this matrix here with 1, 0, then you get the first column. If you multiply that by 0, 1, then you get the second column. So that will span your image. That's why the columns of the matrix representation always span the image. Of course, as the columns are meant in B prime coordinates in this case, you also have to interpret your result in terms of B prime coordinates. What was the last question?
One more. What is the difference of the transformation matrix and matrix representation?
So the matrix representation of linear mapping is more general. The transformation matrix just computes the transformation of a vector between different coordinate systems without changing the vector. In other words, it's the matrix representation of the identity. It doesn't change the vector, it just changes the coordinate system. A matrix representation of a linear mapping like we have here, so this one here, that also changes the vector. So what that does is it takes an input vector in B coordinates, it then applies the mapping F, it changes the vector, and the result is then given in B prime coordinates. So this coordinate transformation is also happening, but also there is modifications done to the vector using this mapping F. So that's the more general case. And if you just use the identity here in place of this F, then you will get the transformation matrix. It doesn't really change the vector, but just the coordinate systems. That's the difference.
Okay, and there is like quite a long question as the last one. It says, I had a question regarding affine subspaces. Professor Ritter said in his videos that an affine subspace is a subset of a vector space, not an affine space. So I suppose there is just vector space, and we define for it either linear subspaces or affine subspaces. Also, he never mentioned affine spaces in his lecture.
Yeah, on purpose. So I guess you're referring to a question you asked on the forum. I haven't gotten around to answering that yet, but I will. Short form here is, we did define vector spaces independently of anything else. We did define linear subspaces of those vector spaces, and we also defined affine subspaces. For us, these affine subspaces always depend on a vector space. They always live inside of a vector space, so to say. So an affine subspace is always a subset of a surrounding vector space. There is, of course, a way to define affine spaces without resorting to vector spaces. For example, you could take a more geometrical approach, and you could ask things like, what is a point? What is a line? How can I define that axiomatically? And then after some more and more elaborate definitions, at some point you get to something like an affine plane and an affine space. That is quite a complex concept, and we're not going to use it here. So probably most vector spaces that we'll use are just subspaces of some r to the n, and all the affine spaces that we're going to use are subspaces of some r to the n. So you can define that in a more general way, but we're not going to discuss that simply because it will not be of any use to us. It's a fascinating theory, but it would just take too much of our time to discuss that.
And there are no more questions.
Good. If you have any feedback concerning this course in general, again, the evaluation is still open. Today is the last day, so we would appreciate your feedback a lot. This is the last official class before Christmas. So I wish you all happy Christmas, happy holidays. Hopefully with some time to relax as well, and some time to maybe catch up on the topics that you might have missed. We'll continue after Christmas and after the New Year. So the next lesson in this course will take place on the 7th of January. That's a Thursday. So we'll go on right away after the holidays with the tutorials on Thursday. And then on the following Monday, that should be the 11th, I think, we'll go on with the central exercise class. Then on sheet number 8. So again, happy holidays. Happy New Year. Hopefully a more enjoyable New Year than this last one was for most of us. And I hope to see you next year then. So Leslie, thanks a lot for moderating.
My pleasure. I also wish everybody Merry Christmas and Happy New Year.